Hi everyone! I'm happy to virtually see you at PGCon online. My name is Andrey Borodin. I'm from Yandex Cloud. I'm leading open source RDBMS development at Yandex Cloud. And this is a talk about implementation details of concurrent index creation. This talk might be of use for beginning hackers who want to know more about internals, or to DBAs who is interested in learning on how concurrent operations may affect database workload. Few words about me. I am doing Postgres development since 2016. Currently, grepping master branch shows that I took part in 61 or so patches as a reviewer or author. Sometimes I'm contributing to Greenplum and some other databases, and I'm maintaining some open source projects with different functionality. Why anyone would need concurrent index creation? Because creating index conflicts with inserts, updates, and deletes, and you just at any given moment you have to pick just one, or you are doing index creation, which is sometimes quite time-consuming operation, or you are mutating, updating, deleting, or inserting into your table. Actually, if you want to know a lot of very neat details about changes of concurrent DDL, there is a great talk by Robert Haas with a lot of technical details and code examples. And this talk is a very simplified version about just index creation. But the talk by Robert Haas have a very good statement of a problem. What's concurrent DDL? This is a change in definition of the object while object is being used. And you are not changing index, you are creating index. Why this is a problem? Because the index is a part of a table definition, and it must be taken into account by planner as a part of a table. And also, when you are creating index, you must be sure that when the index created, it have references to all the running to all tuple versions that are in the table that are created by running transactions. And finally, each transaction modifying data must update indexes too. So running transactions must get to know that index exists to update it. To go further, we need to enumerate transactions, different kinds of transactions that we have. When you are connecting to a database and starting doing some querying, you get so-called virtual transaction, which is a kind of transaction that is not doing any persistent change to the data. And virtual transaction, the identifier VXID is a identifier of a backend and identifier of automatically incrementing counter within each backend. So here you see 6 virtual XID. When you start changing the data or ask for real XID, you get it. This is a transaction ID, which is a global for a database. Incrementing identifier. Here you see 745. And finally, you can have so-called prepared transaction or two-phase commit transaction. The difference between regular transaction and prepared transaction is that prepared transaction stays prepared if a database crashes or is being restarted. So prepared transactions provide you slightly more guarantees of data persistence. If you restart database, all transactions in progress are effectively rolled back, but not prepared transactions. These transactions might hold locks on a table, starting from very simple access share lock taken by each select query. If you observe data within the database, you have to make structure of a table that you are selecting immutable until your transaction is over. And this level conflicts with exclusive lock of a table. If you are doing updates and deletes, you get so-called row exclusive lock, which conflicts with share lock taken by create index. And in the middle we have share update exclusive lock, which is just like row exclusive, but it conflicts with itself, and this lock is taken by table vacuum. So let's talk about indexes more. Indexes are very interesting type of objects within the database. They never affect results of a query. This is per SQL standard. And in Postgres we have so many different access methods. We have bittery, gists, gin, brin, and so on and so on. And also we may have indexes as extension. And infrastructure for creating index concurrently must be shared by each and every access method, each and every access index type. Indexes have identifiers of tuples in a heap, actual rows written in heap table. And if index do not have a reference to some row, this row might be falsely invisible to some transactions. That's why transaction may create an index without some possibly deleted rows, possibly garbage for future use. But if any transaction can see this still can see this garbage, we cannot use put in use this index. So how usual index creation works? We grab a share lock on a table, stop every single insert, update, and delete in the table. We create a tuple in a system catalog, and changing something in system catalog at the end of transaction will force update of caches of each and every backend within the database. Then we invoke index build routine, which is provided by access method. Each access method knows how to create index from the data which is not changed right now. And then we commit our transaction, and index creation with this level of lock is fully transactional. We can roll back it if we for some reason do not want to have this index in our database. But how to create index concurrently? This is essentially the same task, but what's different here? We need to take lower level of a lock, just excluding vacuum. We need to build index somehow, and then start to insert new data from new transactions and validated catch up rows that are missing in our index. And validation is an interesting part of index creation. To validate an index, we are using access method routine index bulk delete. This is actually vacuumization of the index, but not for deleting garbage, but to collect row IDs, CT IDs from that are known to index. And then we call sequential scan on our heap table, but are excluding rows that are already within the index. And for any missed row, we update our index with regular inserts. So what's the algorithm for creating index concurrently? We grab a share update exclusive log, preventing any running any vacuum within the database. Then we create a system catalog record for to prevent creating hot change heap only tuple update chains that are contradicting to this new index. Then we invoke access methods index build routine, and we are making index valid but not ready for usage. This means that now this index can accept new inserts. It must be notified about any new tuple in a table, but it can still be used for index scans and index-only scans. After this, we must ensure that there are no old transactions that do not know about this index. Then we call validation, like catching up with old rows, and then open this index for index scans. That's it. How it's implemented? We see here 3 different barriers marked with yellow, and there are 2 routines for implementing these barriers, waiting for lockers and waiting for all snapshots. Waiting for lockers essentially is the same as grabbing share lock on a table, but it's grabbing share lock for each backend independently. So one transaction that was using index before, that was using table before creating this concurrently cannot continue. It can continue, but it will prevent finalizing our index creation. And within each backend, we must grab this share lock, but it is released instantly. How it is implemented? We are going through all procs in proc array and collect virtual transaction identifier, transactional identifier, and prepared transactions. And then for each log holder, for each transaction that's holding log for a table that we are indexing, we are waiting for a completion of this transaction. And that's it. Wait for snapshot is a very similar operation. We are going through proc array and waiting for each transaction that might see tuples that we consider garbage, and wait for completion of each backend that can see 2 old tuple versions for our new index. And one final thing about concurrent index creation: sometimes we need reindex concurrently. Usually it's done to free up some space, and this is a very similar operation to create index concurrently, but at the end we need to swap indexes and rename new index to the name of old index and mark old one as dead. So essentially here we have the very same algorithm as with create index concurrently, but now we have more barriers, similar barriers taken during index creation. This is how it should work. And now I'm going to tell you how I was hunting bugs. In this this version, it was implemented many years ago. It was in Postgres 8 point something, but from time to time it was causing problems. And here is my story. I first encountered this problem in 2018. At some point in one of our databases at Yandex, we found that INDEX is not seeing one row which is observed by sequential scan. We had a gist index in this database, and index scan was going through the gist index. So basically I thought that B-tree is nothing to do here, and overall infrastructure seemed to be very intensely used. So my initial thought was to look within a gist. And I started with creating support for gist in object verifications. I've created a module that is checking gist indexes and checks that we have all heap tuples indexed by some by a gist index. But using this model didn't show us anything interesting, and I decided, okay, so probably it's some hard to find bug, maybe I will find it later. Later in 2020 we found out that there is a problem with repacking indexes in our S3 metadata database. Why we are repacking indexes? Because indexes after repack empty a lot of quite expensive space, but also they are much more robust, much more performant, and we were doing index repack for every bloated index on a Friday night. Every weekend we have renewed indexes, and this saved us a lot of space. But at some point we found out that some freshly created data in S3 is missing in index scans, and it was very critical for us, so we had to turn off repack. Somehow we found out that the problem in index repacking, and I started investigation. First of all, it was clear that the problem is not in gist, and I've toyed with copy from that was in a workload, toyed with hot chains, tried different approach with prepared statements and system catalogs, and on December 2020 I've created a Go program that was reproducing the problem. That was running concurrent index creation and concurrent prepared transactions. So the problem was at that point obvious, that prepared transactions can own locks. For example, if you update a table by prepared transaction, prepare it, you don't see these transactions in a list of pgstat activity, you don't see it running, but if you try to alter the table, it will wait for the lock. If you add a column or remove a column or try to drop the table, it will wait for prepared transaction completion. And prepared transaction have a transaction identifier but don't have a virtual transaction identifier, which resulted to be quite important thing. Remember this table. So we have prepared transactions and recovered prepared transactions. Recovered prepared transactions obviously do not have virtual transaction identifier because they were created by virtual transaction. They were created by backends of a previously running database, not currently running database, probably a database on a different timeline. But at the moment, 2 years ago, the table actually looked like this. Prepared transaction never had virtual transaction identifier, and that was a problem. we didn't take in account prepared transactions at all because they don't have a weak seed. Get lock conflicts routine returned weak seeds, and virtual exact locked weak seeds, but two-phase commit transactions didn't have virtual transaction identifier, and in January 2020 we with Noamish fixed this problem by returning not just weak seeds but regular seeds for awaiting in a share lock barrier of create index concurrently. And I was happy that we can re-enable our epochs. We did it in after minor release in February, but through the April S3 team of Yandex Object Storage contacted me and notified me that this problem persists. There's still some bug in create index concurrently. I started analysis and it was obvious that we may have a transition from virtual transaction ID through real transaction ID and to phase commit transaction ID. And if we get lock conflicts have a weak virtual transaction ID, when we are doing real locks, this virtual transaction ID already may be converted to real transaction and we will miss it because it was not prepared transaction at the time of scanning locks, but already was prepared transaction when we were locking it. So in May of 2021 I created reproduction with just 3 PSQL concurrent PSQL sessions. You could create a situation when concurrently created index is locking in index tuple for a heap tuple. And the first idea to where to go was to create a tab test, parallel tests for this, so that we could randomly test create index concurrently implementation on a build farm. But the problem was reindex concurrently is conflicting with itself, and it was quite difficult to implement these tests. And when I finally got it, I've got parallel tests in June 2021, I found out that my fixes just don't help. We still have this problem with incorrect indexes being created by create index concurrently. And doing researching further, I found out that the problem was appearing not just in the presence of prepared transaction, but may appear with regular transactions. And Noamish helped me with this and diagnosed that the problem was in a relation cache. What's relation cache, by the way? Relation cache is a cache of table structure within each backend. Each backend have its own cache of tables that this backend is using. And we have sys caches. This is the caches of different for different tables in the system catalog, and one specific relation cache which captures structure of a relation, structure of a table with its indexes. And the algorithm of building relation cache is as follows. First, when we are first using some table within our transaction, we grab we check if there is a shared invalidations, like messages from other backends that our cache may be stale. If our cache is stale or we just don't have this table in our real cache, we construct relation description by reading system catalogs and put constructed description to the cache. And if we are doing some changes concurrently with locked table, if we are doing DDL, we at the end of the transaction we put shared invalidation message to queues of our other backends, and then we release a lock. So this is a basic invariant that if you didn't hold the lock, then you must check invalidations. But you can see here that here is a problem. There is time of check to time of use race condition. In some cases, if you are processing, if you are creating a relation description of a table while you are already creating relation description of other table. So if you are recursively calling relation build disk, one of shared invalidation consumption messages may consume message of another table, and you can put stale relation description to your cache. Noah fixed this by creating stack of so-called in-progress invalidations that help you to avoid this situation. And this fix solved the problem of concurrent index creation without prepared transaction. But by the September of 2021, prepared transactions still were working concurrently created index. And the problem, one of the problems that I found was that we are converting virtual transaction to real transaction. We must take a lock for the transaction. You always see your transaction ID, your XID, within PG logs. But we first start to advertise our XID in proc array, and only then we grab a lock for this XID. So essentially XID is starting to exist before it's locked. And that was a problem. We couldn't easily convert virtual transaction to real transaction. If we saw some transaction as a virtual transaction, we have to lock its virtual transaction. And another problem was found that when we are preparing a transaction, we have to move locks from one proc array item to another proc array item, because regular transactions are the prefix of proc array, and prepared transactions are suffix of proc array without overlap. There are other backends, by the way, between them. And in a code of prepared transaction, we were first clearing transaction logs and then adding these logs to the prepared transaction. So there was a moment when logs were not held by any transaction. And this was easy to fix. We just flipped lines of the code in prepared transactions, and this finally solved the problem of tests. So how share lock barrier is working now? If we want to have this wait for lockers function, we are waiting we are first collecting all virtual transaction identifier and all regular transaction identifier. Wait for each virtual transaction ID. If it is converted to regular transaction, collect this and wait for each regular transaction ID. And then for each transaction identifier which was prepared transaction, we are trying to look up for virtual transaction ID in proc array, waiting for each newly found seed created by Vixid. So by October 2021, fix was pushed, and we re-enabled Repacks on S3 and are happy to use it, and now it works just fine for us. But it wasn't the end for this story. It immediately resulted in some build farm failures, and I was investigating what's failing there, and this resulted in fixing some Dragonfly BSD. Thanks to Thomas Monroe and the community, we had to fix FreeBSD to run these tests. In fact, this bug was most complex bug I ever encountered in my life. And I was fixing this for 9 months continuously, sometimes interrupting for other works, but at any given moment of these 9 months, I had a test and could not just fix it. I tried RR, replay and record and replay debugger, but it didn't help me, unfortunately. But still, it's a great piece of software. The fix was pushed 4 times with 6 reviewer, and tests for this bug triggered kernel bugs in 2 operation system kernels. But still, it's not the end. We know that there is a problem on standby currently, and this is a work in progress. At some point this will be fixed too. And a few days ago, somebody at PGCon Hackers reported that still there are observed some corrupted indexes in presence of regular transactions, so essentially investigation is still going on. Still, this is a great functionality. Currently we use it in production very extensively. Each weekend we are rebuilding most of our indexes, and it works like a charm for us. If you have any questions, feel free to contact me anytime via email or maybe Telegram. And if you have questions right now, I would be happy to answer it. Thanks for watching.